I'm Yi-Hsiu Chen. I will talk about some computational notions of quantum min-entropy. This is the joint work with Kai-Min Chung, Ching-Yi, Salil, Vadhan, and Xiaodi. So I will start with giving some motivation about why do we study these computational notions. And then I will define what is computational quantum min-entropies and state our main results about that. After that, I will show you some interesting discovery about even more general notions called computational quantum relative min-entropy. Okay. So let's briefly review what is the leakage-resilient cryptography. Usually in the theoretical research in cryptography, we will make some assumptions implicitly. For example, we will assume the adversary can only access some information in a black box way. However, in the real world, that might not be the case. For instance, in the chosen plaintext attack model, we allow the adversary to make many queries on the input it chooses, and it will learn the corresponding output. So basically, we assume the adversary only learns about the input and output pairs without any further information. But in fact, during the computation on those inputs, some information might leak. For example, the running time, the power consumption, the radiation. And this sort of attack, we call it side-channel attack. So leakage-resilient cryptography wants to solve this problem. And in this work, we would like to consider even more general leakage, which is a quantum leakage. Even though we don't know any concrete information that is counted as a quantum leakage, but usually in the leakage-resilient cryptography, we won't make any assumption about what kind of leakage we have to deal with. The only assumption we make is that the leakage will be very short. If you leak lots of information, then there's no hope to construct a security system, right? Now, let's consider a specific primitive, stream cipher. So stream cipher is just a function SC, and we'll iteratively apply the function SC on an internal state. In the ith round, say the internal state is Si, and after applying SC, it will output, the internal state will evolve to become Si plus 1, and also it will output the bit string Xi plus 1. And we hope that Xi plus 1 looks pseudo-randoms from the point of view of an adversary, even the adversary knows all the outputs before the ith round, that is x1 to xi. So far, it's the definition of the ordinary stream cipher. In the leakage-resilient stream cipher, we consider the case that adversary learns more than just x1 to xi. So during the computing xi plus 1, because you are computing on the internal state si, so we assume adversary will learn some information about Si. We call it Bi. So as I mentioned before, Bi is just some short information, and we don't know what kind of information it is. So to prove the security, basically we want to show that the X retains high uncertainty even after the leakage B. And the way to formalize it mathematically, we use the entropy notion to capture the uncertainty. So we hope that condition on B, the entropy amount will only lose like the length of B. And we call this inequality leakage chain rule. So basically, we want to show the leakage chain rule about some sort of entropy notions. In the classical case, if we plug in the H, we plug in the mean entropy as H, then the leakage chain rule holds by definition. But in the leakage-resilient stream cipher, xi is just pseudo-random but not random. So we have to consider the computational notion. And turns out leakage chain rule also true in the computational min-entropy notion. And as I mentioned about our motivation, we would like to consider the quantum B, the quantum leakage B. So in the quantum case, the quantum min-entropy, if we consider quantum min-entropy, the leakage chain rule also holds. So our main question is about how about the computational quantum min-entropy? So in this work, we defined what this computational quantum min-entropy is, and then we show the leakage chain rule also holds in that case, and then apply that in a leakage-resilient stream cipher against the quantum leakage. And by the way, so in the quantum case, we measure the size of leakage using the number of qubits. Now let's define the entropy notions. We start from the most basic thing. So basically, min-entropy capture the worst-case unpredictability of x. These three statements are equivalent. So we like to emphasize the third one, it's an operational definition. So the random variable x has entropy at least k if and only if for any algorithm it cannot predict x better than, with probability better than 2 to the minus k. And in the conditional min-entropy case, we consider a joint distribution xb. We want to measure the amount of entropy x condition on b. And its corresponding operational definition is you give the b to the adversary, according to b will guess x, and still it cannot guess x with success probability greater than 2 to the minus k. Now let's move on to the quantum definition. In the quantum case, instead of consider the joint distribution xb, we consider the bipartite state rho xb. And we only consider the case that x is still classical, but now b can be quantum. Koenig, Renner, and Schaffner, they show that for CQ state, the operational definition can be extended to this case. And what the adversary can do is it can do some measurement on B and then guess X. So most generally, A can be expressed as a POV and matrices. Then that's just the formula of guessing probability. So far, the notions that I have defined are information theoretic. So now we move on to the computational notions. We hope that the computational notions can capture the unpredictability from eyes of a, say, polynomially bounded adversary. And there are plenty of computational notions, but in this work, we will focus on we call it Hell entropy, which is the most common and could be and a useful one. In the Hell definition, we say rho xb, x condition on B has high Hell pseudo-entropy if we can find another quantum state, rho prime xb, that rho prime xb has a real high mean entropy, and rho xb and rho prime xb are computationally indistinguishable. So basically, rho xb itself, it doesn't have high mean entropy, but it is indistinguishable to some high mean entropy states. Okay, so under this notion, this is our main result. So when I mentioned the motivation, I cheated a little bit on the leakage chain rule. To prove the security of the leakage-resilient stream cipher, we actually need a leakage chain rule that contains the prior knowledge Z. So now Z appears everywhere. And we're able to show that the leakage chain rule also holds in the quantum Hill entropy, and in the case that B is quantum, but X and Z are still classical. And by this leakage chain rule, we can show the existence of a quantum leakage-resilient stream cipher. However, because we can only handle the case that Z is classical, that's why we have a restriction about the memory of an adversary, the quantum memory of the adversary. So if we can show that when Z is quantum, the leakage chain rule also holds, then it's likely that we can prove something better. We can remove the restriction on the adversary. So to show these results, these are our main techniques. So the matrix multiplicative weight update method basically helps us to switch the quantifiers. So I didn't define the matrix entropy, but matrix entropy is basically similar to the Hill entropy, except we switch the quantifier. We say that for every distinguisher, there exists a quantum state that is indistinguishable by that distinguisher. And because multiplicative weight update method can imply the min-max theorem or the min-max-like statement, which help us switch quantifiers. So we are able to show the equivalent between Hill entropy definition and matrix entropy definition. And that will help us to prove the leakage chain rule. Okay, so these are our main results, and it's about the computational min-entropy notions. And we study an even more general notion, the relative min-entropy. So this is the definition of relative min-entropy. Is just an information theoretic notion. So this definition is kind of cryptic. Let's see the operational interpretation. So basically, the relative min-entropy measures the worst case distance between two states, two quantum states, rho and sigma. And we say the distance between rho and rho from sigma is at most lambda if you consider any event A on the quantum state, and the ratio between A of sigma and A of rho is bounded by 2 to the lambda. And why I said it's a generalization of the min-entropy is due to the below equality. So if we replace the sigma by a maximally mixed state, then the relative min-entropy basically is just n minus min-entropy. So now let's try to generalize this notion to the computational case. Since we are considering two quantum states, so there are at least two ways to generalize it. First, we can change the state rho. So we say the distance, the computational distance between rho and sigma is at most lambda if you can find some rho prime that the true distance between rho prime and sigma is at most lambda, and rho prime and rho is computational indistinguishable. Similarly, we can replace the sigma by sigma prime. So we have two definitions about the computational relative min-entropy. So what's the relationship about these two definitions? In the classical case, the dense model theorem actually saying the Hill-2 entropy the second type of computational notion implies the first type. And in this work, we also show the first type also implies the second type. That means in the classical case, these two definitions are basically equivalent up to some parameter loss. An interesting thing is that in a quantum case, we actually can show a separation. We found a quantum state rho and sigma such that the first type distance is at most a constant, while the second type of distance is just a constant, but the first type distance can be infinity. For a little more detail, for the construction, we use an important and interesting observation is that there exists a pseudo-random pure state. So we will take sigma as a pseudo-random pure state, and so the rho prime just just a random state, or say maximally mixed state. And rho is a state that very close to sigma prime. And now the question is whether we can also find a rho prime that is computationally indistinguishable to rho and then have a small distance to sigma. But an important observation is that the only state that can have a bounded distance to a pure state is pure state itself. So in that case, rho prime is forced to be the same pure state as sigma. However, if rho prime is just a pure state, then we can easily distinguish rho and rho prime. So that's why it has the first type of computational distance between rho and sigma is unbounded. Okay, so that's all I have. So for some open problems, as I mentioned, the most important open problems from this work is to make the leakage chain rule also holds in the case that Z is quantum. And we believe that that can help us remove the quantum storage restriction. Also, we defined some computational entropy notions, and we would like to see more studies and applications or other properties of those computational notions. Thanks.